Welcome to the AI for You Cafe for live presentations around AI. Today, as you may see, we welcome our speaker, Christian Gamrad from CEA from France. Hi, Christian. Hi. And as always, we are starting slowly, so we give all the participants a chance to join us. Just that you know your right place. The title of today is Neural Network Design and Deployment for Embedded AI. My name is Carmen McWilliams. I'm the moderator and organizer of the AI for You Cafe. I'm the director of the company Grassroots Arts and a partner in the European AI for You project. So please take notice that this session will be recorded, and you will find the link for the recording later on our platform and in the AI for You channels like YouTube or GoToStage. No confidential information shall be shared in this cafe session. All speakers express their personal views and opinions. This is not the official AI for You project opinion necessarily. And our web cafe offers a series of live web sessions. The cafe is an online forum to gain insight into the European AI scene. Participants get the chance to share knowledge and experiences and meet stakeholders from various areas of AI research and application. So today we're coming directly to Christian because I want to introduce him. Christian is Chief Scientist and CEA Fellow in the field of Advanced Computing Architecture. Graduated from the University of Grenoble and INSAC in Electrical Engineering and Information Processing. He began his career at CEA Grenoble in 1981 on data processing projects for nuclear physics experiments. He got involved in the study of neural networks in 1987 and led the team of the MIND 1024 neural computer project in 1989. He joined CEA Saclay in 1995, where he worked on the development of massively parallel computers for image processing. In 1997, he started an activity on reconfigurable computing and later on initiated a research on novel computing paradigms aimed at nanotechnologies. Christian has coordinated several national and European funded projects and has contributed to more than 60 papers and book chapters. And again, welcome, Christian. Thank you for joining us. And I think we have now our audience is there. As you know, it will be always interactive. If you feel like asking after the presentation questions to Christian, please use the control panel on your right side. There you can find a text chat and a place for your questions, as well as you may raise your hand. There's a hand symbol, and I see it, and you can afterwards also ask the question directly. But now I want to give the stage to Christian. Hi, Christian. It's now you. You can present your presentation and maybe say first a word to the participants.
Okay, thank you very much, Carmen, for the introduction. I hope that everybody can hear me nicely, because we have some problems setting it up, but now I think it's working. Anyway, so as Carmen said, I'm kind of an old fellow since I started my career about 40 years ago in nuclear physics, which is not artificial intelligence, but anyway. I've been dealing with computers and computing for all of my career. And today I'm going to speak about artificial intelligence and specifically embedded artificial intelligence, which is of special interest for our department, for our division, and some of our laboratories. And I'm going to tell you about some tools that we've developed and also some architecture and chips that goes with it. But I'll try to be a bit not very specific or technically specific, because I don't know about the audience, so I don't want to be too technically detailed, and I prefer to focus on the rationale, the objective of our work, and how it helps people design chips for artificial intelligence and what it could be, how could it be used for. So I'll just jump into my presentation. I'll try to make it maybe 35 minutes, 40 minutes, and then have questions if people likes it. Okay, let's go to the presentation.
Thank
okay,
you.
so hope that everybody can see. Okay.
Thank you.
All right? Okay, the neural networks design and deployment. So N2D2 is the name of a tool that we developed at our place. So I'm Christian Gabra. I'm the old guy. I'm now chief scientist, and I was leading the team for a long time, a few years back. But now the team is made of mostly young fellows that are really into the programming and the modern way of dealing with things, and they actually did the job actually. So I'm really reporting their job in this presentation. So Olivier Bichler is the head of the development of N2D2, together with David Briand, Vincent Laurent, and many others that contributed to this to those various tools and frameworks. So in the future, if you need specific questions on, you have specific questions on technical details, it's better to go to these people. Okay, let's go. So, oh, sorry, here it is. So the outline of my talk, I will just go back to a brief introduction on artificial intelligence and deep neural networks. Then I'll focus on what we call embedded artificial intelligence and how do we define it in comparison with the general deep neural networks and artificial intelligence. Then I'll focus on the N2D2 platform and what it is, how can it be used. I will also focus on P-Neuro and D-Neuro, which are two architectures that we developed and that goes hand in hand with the N2D2 platform. And then I'll finish with some new features that we are working today for N2D2 and advanced concepts of the framework, and we'll wrap up. So I think I'll try to be something like 35, 40 minutes. Okay, introduction. The artificial intelligence is used, or you know that it's been booming in 2012 or 2010, where deep neural networks resurfaced the world. Also, it's been a very old story because all the principles of deep neural networks and the artificial intelligence as we know it in 2020 were actually laid out in the 80s or 1980s and 1990s. So that's last century. That's a long time. So all the principles of neural networks, backpropagation, deep neural networks were laid out quite a long time ago. But today it gives some very good results, like the ImageNet classification example or the Facebook DeepFace program, which led to a very interesting results, such that various implementation of deep neural networks give way to a very good performances. You can see here that the performances of those various networks have been quite impressive, like 99.8% to the handwritten digit recognition task, but also for more complex tasks like ImageNet, up to more than 80% recognition rate, which is quite good when you compare it to what a human mind can do on the same task. So it's really comparable, and in some places it's even better than what a human can do. So the performances of those things led to various applications, such as pixel image segmentation. Like here, you want to you want to differentiate, for example, the road from the pedestrians and cars and buildings. or you can also use the same deep learning application to recognize cars in the street, like on this little video where you can see that bots are following the cars, and this is all done by deep neural networks. You can also use it to you can also use it to do super resolution or image compression, which is the same thing. Either you decrease the number of pixels when you want to compress, you decrease the amount of information, or you want to increase the amount of information when you want to do super resolution. And convolutional neural networks and deep neural networks have been used for this kind of application. Oops. And the score and the results of such deep neural networks has been quite impressive over the year, and the progresses of various types of networks. But at the same time that the performances got better and better with different architecture of networks, the complexity and the amount of computation that needs to be done also increased a lot. And those the radius of the circle gives the amount of computation needed to yield the accuracy that you can see on this axis. So you can see that there's a kind of a relation between the increase in performance that you want, but also the increase of computational power that you need to have this increase in performance. So it means that you need more and more computing power to give those to obtain those performances. And the basic building operation of any neural networks or any deep neural network is the same. It's been the same for the last 40 years, the last 30 years. So it's basically a convolution kernel that you have various coefficients for this kernel. Here it's a 3 by 3 very little kernel, and the idea is that you just slide your kernel over your image, and for each position of the kernel on the input image, input map, you compute an output feature map, and you compute a complete map. And you do that over and over for all the pixels of your input image, and then you obtain a various output feature map. You do that over and over, and then you build a deep neural network. You put several layers. For example, here the input layer, then the convolution one, a layer for pooling, another layer of convolution, another layer of pooling, etc., etc. And the number basically the number of layer qualifies the network as deep. If the number of layer is very, very big, say it's traditional early neural networks are only 3 layers, but now it's very frequent that we have neural networks with more than 10 layers, and they are called deep. You can even have networks with more than 80 layers. So that's the deep qualifies the number of layers that you have on your network. But those networks you can understand easily if you need to do this amount of operation over all the the convolution kernels of all the images, of all the layers. It requires an enormous amount of computation. And that's one of the problems. How do we deal with the amount of computation? Now, just to give you a broad view of all the actors and the people working in this field is very broad. It ranks from academics to industrials, and there's a lot of people doing several things. So going back to the idea of computational power is, of course, the more complex the task you want to solve with the better performance, the more computational power you will need. And the problem is that if you want to embed or to integrate this computational power inside everyday objects, you will get into trouble. Everyday object is something like a smart sensor, for example, that gives sense the world, that sense temperature or position, or a camera or a microphone. Then it will make some info. It will produce some data. Data will go into the internet. Internet will go into some web server, and then some backend processor or backend computer on the cloud or HPC will analyze those data and transform that into information, provide some services, and eventually will go back to the smart sensor to fine-tune the parameters of the smart sensor, and then the smart sensor will, and then there's a loop. The problem in that loop is that the raw data is transformed into information at the cloud level. Why? It's because of the complexity of artificial intelligence algorithm, the complexity of deep neural networks, because it needs a lot of computing power that is found usually on HPC platform in the cloud. So it's not very practical to have this loop going from smart sensors that are maybe on a watch to the internet and to the cloud. We'll need something to abstract the information processing as soon as possible. We'll need to transform data into information as early as possible, and if possible, right into the watch, right into the sensor. The problem is, how can we bring in a HPC computer into a watch? That's the key problem of embedded intelligence or embedded artificial intelligence. How can we fit this computing power into such small object? That's what we call, what we define. It's how we define embedded artificial intelligence, or we can also call it edge intelligence or edge processing. So embedded intelligence is very needed. For example, in very critical applications such as a car, when it's in a situation where the driver needs to brake, if the decision of braking is the result of an AI algorithm, it cannot go through the cloud because it needs to make the decision locally. So safety will impose that some critical functions should be computed locally. So we cannot have a link to the cloud for safety critical functions. So we cannot also put a high performance computer in the boot of the car. Or if you do that, you can't take your suitcases to go to holiday. Also, another kind of application is embedded intelligence for example, at the home, or to detect, for example, what the reason here is not it's not the same as for autonomous car. It's for privacy reasons, because the images that the camera see can be very private. We don't want those images to go into the cloud. So we want to process those information locally. So this processing also will require embedded intelligence inside the camera. For example, with minimum power and wiring. For example, we've developed this application where it's a deep neural network application that automatically detects if a person is lying, is standing, and then it can trigger an alarm if the person is lying. But of course, this kind of application needs and requires local computation, local data processing. Also, there's a problem of bandwidth and cost. If you have all your processing power in the cloud, you need a lot of bandwidth and network facilities to connect your local processing or your local application to the cloud. And then it's a waste of of energy just to send images. So you really need to for those applications to do the processing locally. A last but not least reason is that if you when you use generic processors such as those that are found in HPC or in the cloud or in cloud servers, CPUs or GPUs, they are quite inefficient in terms of picojoule or energy unit per flop per basic operation. See, a GPU is a bit more energy efficient than a CPU, but both are less efficient than a fixed function or a custom design function. So there's also a requirement to design specific chips for specific needs to gain a better energy per operation ratio. So that leaded us to study various design frameworks of deep neural network that exist in the world, and you know almost all of them. When you want to design some kind of deep neural network or intelligence artificial application, you maybe you use TensorFlow or PyTorch or Torch or Caffe or Theano or Keras or scikit-learn, name it. There's a lot of them. And then you will try and play and start playing with your application and see what you can do with those deep learning frameworks. That's very, very useful because it allows you to play and test with your ideas of applications. But once you're happy with that, and that you say, okay, I'm happy with that, and I want to design a specific chip for my product based on based on what I've experimented with those frameworks, then you're a bit you have a problem, because those tools also, they are very useful for exploring and playing with artificial intelligence. They are not very adapted to design a specific chip. That's where came N2D2, and that's where N2D2 lies in between the deep neural network, the general deep neural network that I just described, and the idea of building specific chips for embedded application. So the motivation for N2D2, it's just what I said. Deep neural networks is a very good tool, a very good way to implement artificial intelligence application. It's very powerful. It can be used for a lot of different applications. So it's nice, but it needs a lot of computing power. If you want to do that on embedded chips, and you want to design your specific chip for a specific application, then you need a tool that is up to the task, and N2D2 tries to fill that need. So I'll just go briefly on that, but it will allow you to explore with various targets and various ways to implement your deep learning application onto either a generic hardware or specific hardware that you will need to design. So N2D2 will allow you to balance speed and power, and to see to make the compromises that you need for your application, depending on the budget, the power budget, or the network bandwidth budget, or even the weight or cost budget that you have for your application. Okay, so N2D2 is a short name for neural network deploy and design. So N2D2, it's a platform for the design and exploration of DNN applications on specific target hardware. So in N2D2 is there is two parts actually. There is a front end part which resemble a lot of what you have in TensorFlow or PyTorch. It's a purely software part which allows you to connect to learning, test, and database. to do data conditioning, signal processing, to optimize various algorithmic parameters, to choose the algorithmic the learning algorithm that you want to use, to choose the nonlinear function that you're going to use, to define the number of layers, the number of the dimensionality of your kernels, and all your connectivity within the network, and to do the learning, and then to test that. So it's this part of N2D2 is quite similar to what you will find in scikit-learn, TensorFlow, PyTorch, Keras, you name them. So it's very similar. But N2D2 is original because it has a second part, which is an implementation part. So this second part is the more interesting, the more specific or the more original to N2D2, is that when your network has been trained and when you're happy with it, you can do a code generation and a code execution path. That is, you can decide to run your optimized and your trained deep neural network onto either generic CPUs or generic GPUs, but also to specific hardwares, like many core CPUs, like Calrays or various MPSOCs, or GPUs or FPGAs, or even specific hardware accelerators, such as P-Neuro and D-Neuro. I will come to that later, and even future hardware accelerators or platform. And that is very specific to N2D2. So N2D2, the first part, the data exploration part, has one very interesting, well, has been sophisticated in one specific aspect, is the aspect of the data, what we call data conditioning. It's the front end to the N2D2 platform, which allows you to define a specific way to see your data. For different applications, you will have different sets of data. And of course, that is very important before you start designing your deep neural network application, to know about your data, to have the knowledge of what your data set means, what they are used, what they will be used for, and what are the dimensionality, the number of example, lots of different things. N2D2 will allow you to adapt the front end of the tool to various types, various geometries, various topologies of data. Whether it be images, so it's 2D images, 2D two-dimensional data, or signals, which are time-based, event-based data, or even n-dimensional types of data. So N2D2 has several tools, several APIs to help you extract the data from your various data sets, and also to partition your original data set into learning set, test set, and various batches. So the N2D2 typical output of N2D2 is, I would say, is not user friendly at the network description file. Like any other platform, it starts with a network description file, just like TensorFlow or PyTorch. They have all their own way of defining the networks, either through programmatically through a Python or Lua script. Here in N2D2, we use a simple ini file, description file, where we define the various the database, the input database, and also the geometry and the topology of the network, the number of layers, the dimension of layers, where the layers, how the layers are connected, between how the connection is made between layers. Is it fully connected or not fully? Also the activation functions of each layer, etc., etc. So all this is done through an INI file, which is kind of old-fashioned way of describing things, but well, it's kind of very machine friendly actually. So from this file description, from this network description, that is the input of N2D2, you will have several tools at your disposal to do various things. The first tool is a data flow visualization. For example, it will produce a map, a graphic representation of your INI network description file. You will also have some layer-wise memory and computing requirements per layer, and that is unique to N2D2. I'll come back to that later. You will have also visualization tools to help you visualize your data set. Of course, if your data set is not images, but maybe it's a spectra of some signals, you will also visualize that. If it's images, you will visualize like images. You will also have some reporting on the weight matrix and confusion matrix, various tools to visualize and report on the inner weight matrices and confusion matrices, all kind of intermediate results that you have into your networks. And also you'll have various statistical analysis tools to help you define or spot where your application might have some problems or progress to be made. So, for example, there's one very important analysis tool in N2D2. That's what we call the complexity analysis. Complexity for us, because we are computer architects in our lab, it means the computational complexity, and that is because for embedded for embedded hardware target, this is very important to know which is the amount of memory, the amount of buffer memory in between layers, and also the computational needs of each layer. And we can do that layer by layer. So this thing will, for example, in this example, it will tell you that, oh, you have a peak here between layer 15 and layer 16, then you probably have a problem in those layers. But on other layers, maybe layer 3 and 4, you have a problem of buffer memory. That are the memory that links the various layers. And here you also have a problem, but in computing power. So those analysis tools will help you spot the places in your network where your target implementation does not fit completely your constraints in terms of either performance or latency or computation in general. And that will help you design your network in another way, in a different way, to help minimize those bottlenecks. That's very important to be able to do that if you want to have the best possible embedded implementation of your network. Of course, the visualization analysis tool are quite, you can find that in other tools where you can see various visualization of either weight matrices or confusion matrix. You can also have visualize the images with the bounding boxes, the region of interest of the features that you want to classify. But that is it's also available in N2D2, but not original to N2D2. You also find that in other tools. So N2D2, in short, and that's very important, it will allow you to do what we call DNN exploration. DNN exploration is the step you need to make in order to have the best possible implementation of your network. You want to be able to change your CPU, the number of CPU, the amount of memory, and you want to analyze those changes and you want to see what effect those changes will have on the power budget, on the performances, on the latency, on the network bandwidth, etc., etc. All that is very important for the performance of your product at the end. And that is what N2D2 is. So you first build your network using it, then you learn a database, you analyze your network performance, and then you do the implementation. And then at this type, once you have this implementation of your network, you can target various hardware, for example, parallel CPUs, core standard x86 processor, or ARM processors, or standard GPUs, or FPGAs, or even specific hardware. And then you can compare and make your decision. And you can do that quite quickly and decide in a relatively low amount of time. When I say relatively low amount of time, it means a few weeks, I mean. But in a few weeks work, you can say, okay, the best bet for my application is this target. And that can save you a lot of time and budget when you want to go into production of a real application. That is really important when you are targeting a real application. For example, an industrial use case of N2D2 has been used in a rolling mill to detect a defect on its rolling steel, and we have cameras, very high speed, so of course it's very high temperature, and we want to identify defects on the steel, the pieces of steel at in real time, and it's going at a very high speed, 20 meters per second. It's also high temperature, so you can't really stop the factory. So you have to do that very quickly to detect the defect. And here, for example, you have different defects in green, blue, red. That some defects will be really harmless for the steel, but some other defects might need to stop the rolling mill or something like that. And that has been done, all this application been done with ArcelorMittal, and is actually been done with N2D2, the analysis and the implementation. So in short, N2D2 has the ability to target several GPUs, CPUs, FPGAs, specific ASICs, and also, I will come back to that later, specific and more advanced users like Spike computing. So we have developed and we are working a lot with various partners. Of course, we have basic partners that actually like Global Sensing, ArcelorMittal, Valeo, Reflex, and also FT, Microelectronics, with which we have developed most of the basics of the implementation and the analysis part of N2D2 on their application and with their own targets. For example, Global Sensing is developing its own hardware accelerators, and we have developed a specific module to target their accelerators. Other partners are more in the academic world. We'll use them as a research tool, and some others are also looking at N2D2. We'll come back to that later. So just a very sneak peek at our homemade hardware accelerators. P-Neuro is a neural DSP processor that we've designed, and we've designed both P-Neuro and D-Neuro. We'll see the difference as part of the N2D2 framework. You don't see N2D2 as a software, and then there's the hardware besides, but it's all of the software and the design software and the hardware accelerator they're all been designed and developed all together. You know, we've developed the hardware accelerator with the design tool in mind and vice versa. So P-Neuro is a fully programmable hardware accelerator. So it's a fixed hardware accelerator. So it's designed to be clustered as a SCMD architecture. So you have several neural processing elements with a system bus, and all this is targeted to be implemented in a specific custom chip. So it's able to do a very low energy processing computing power. So, for example, if you compare P-Neuro integrated into an ASIC using FDSOI technology from FT, it's capable of dealing with 25,000 images a second with quite so it's quite a high throughput. So it's a performance around 125,000 images per watt, per second, and per watt. So the energy efficiency of P-Neuro when compared to a standard ARM processor is 100 times better. So that's because it's a specific architecture implemented in a specific hardware. It's not programmable, of course. Once it's been burnt into the silicon, it's there. It's not programmable. But when you need this amount of energy efficiency and integration, that's unbeatable. Then N2D2 will allow you to detect if your application needs that or not. So it will direct you to the best possible solution. So P-Neuro has been implemented into FDSOI 20 nanometer test chip. So into this chip that is here. So it's a very energy efficient implementation of an accelerator. But of course, it's not for every application. Only applications that really need that kind of energy efficiency will benefit from P-Neuro. Another accelerator is D-Neuro. D-Neuro is completely different. It's not meant to be embedded into or it's not meant to be integrated into a specific chip. On the contrary, D-Neuro is a library. Actually, it's a hardware library for FPGA. It's just like the ARM processor. It's an IP library that is aimed at being implemented into any hardware. You could, if you wanted, implement D-Neuro into a specific hardware, but it's not really meant for that. I'll come back to that. It's more targeted towards FPGA platforms, where you can have the choice to implement your D-Neuro processors into various forms. And the idea, the core idea of D-Neuro is that it functions at data flow modules. That is, just like, for example, a memory cut can be tailored to different memory needs. For example, if you need, for a specific application, you need words of 64 bits, okay. So you design your memory as 64 bits words memory. But for another application, you might need 128 or 256 memory words. Then you will have to design your memory into those different constraints. D-Neuro is the same. You can design your array of neural network accelerator the way you want. Either you can parallelize the computation any way you want, depending on the type of data you want to process. And that is the real strength of D-Neuro, is that depending on the processing you are going to do, then you will have the possibility to tailor the D-Neuro library or the D-Neuro processor, the D-Neuro accelerator, to whatever topology is needed for your application. And that is where the couple of D-Neuro and N2D2 comes really shines, actually. N2D2 really shines when you have such a very flexible hardware target, because then you can change a lot of things. For example, you can, if your your constraint for application might be the latency. Say my real constraint is the latency of my application. Then you can make several choices. Say, okay, I want to have more processor. Then I know that will have a lower latency, but then it will cost me more. And then I have a trade-off to do between the latency that is acceptable for application and the cost I can put into my target. Then N2D2 will allow you to find the sweet spot in your application using its analysis tools to find the sweet spot. And then once you find the sweet spot, to target to implement the absolute right chip or the right implementation for our application using the D-Neuro library. So the D-Neuro library has been demonstrated, for example, with several FPGA platforms. And for example, we've made an application example, an FPGA demonstration of an application that actually detect and identify various feature maps on the Google Map satellites images. So N2D2 plus D-Neuro is really something made together. N2D2 and N2D2 and D-Neuro, they really go very well together. Also, because of the fact that N2D2 is also compatible with other frameworks, I'll come to that just after that. It also allows to have a more complex and more complete design flow for the deep neural networks applications. So I'll first come to that with next and advanced features. So one of the next feature that is being implemented in N2D2 is the ONNX model import. So ONNX is a Open Neural Network Exchange. It's an open standard for machine learning, and it's an open standard to define neural networks machines or neural networks. So ONNX is compatible with most of the frameworks like TensorFlow, scikit-learn, PyTorch, etc. And N2D2 will be very soon compatible with ONNX. That will give people the opportunity to start a design when they are not sure what they are doing. Maybe they will start with PyTorch or with Keras or with scikit-learn. And then once they are confident enough with their design, they'll say, oh, now my design is good enough. I would like to make a chip. Then it will be time to switch from TensorFlow or PyTorch to N2D2 to target a specific chip. And then it will be possible to do that through ONNX, to export an ONNX model from PyTorch, for example, and import it into N2D2 for further processing. For example, there's a lot of ONNX model available freely in the on the internet. All the the SqueezeNet, the AlexNet, GoogleNet, Caffe, Inceptions, etc. All the traditional and well-known neural networks models are available as ONNX models. So ONNX model, that's a basic the basic feature. You also have free available visualizer for an ONNX model. So that is so that's a feature, and this is the implementation file of N2D2. So that will expose some ONNX. That's a feature that is being introduced and pushed to the next release of N2D2 that will be available soon. Another use of N2D2 is also as a research tool for advanced network model like spike coding. For example, we like spike coding because spike coding has the possibility to be very energy efficient, even more energy efficient than standard CNN. So it's really very it's a very good candidate for very low energy neural network processing, spike coding. So spike coding, we've developed the idea that any standard neural networks model can be transformed into its spiking or rate-based equivalent. So there's a one-to-one a one-to-one correspondence between the two. And then spike coding results have shown some very efficient, very impressive results. That's some results that we have obtained a few times ago in the lab. And also what is very important with spike coding is once the network has learned, the activity within the network is very low when compared to a standard neural networks. And that's where comes the very energy efficient performance of spike coding. So spike coding can be used and can be into N2D2. N2D2 has a module for spike coding. It's really a research tool. It's used by academics to, and it's also possible to develop specific models, specific synaptic models, for example, into N2D2. So I'll just wrap up because I think I've been very talkative as usual. So N2D2 framework is really a world actually from that allows you to evaluate your use cases, your applications, and to try and evaluate what kind of targets you want to for your application. Maybe you just need a standard PC with a standard C code and standard Python. So it's all right. You can just PyTorch for that. But maybe you will need some specific hardware. Maybe you have some very specific power constraints, etc. Then N2D2 can be used to that. So the key message is that N2D2 is really a framework for embedded artificial intelligence. It's not for everything AI. It's not PyTorch. It's not TensorFlow. It's really it really shines on embedded AI. It also shines in allowing to explore various implementation and choose which is the best for you, and you only can tell which is the best for your application. So also N2D2 targets several hardware, FPGAs. Also we have specific modules for ST, Renesas, and Carre. Or of course the own target accelerators of CEA, PNeuro and DNeuro. So we have an ONNX compatibility coming in, and also N2D2 is useful as a research platform for advanced concepts such as spiking network, but also others. So N2D2 is available. It's open source. It's on GitHub. On the GitHub, there's also a number of examples, object recognition, fast detection, road detection. So that's part of the package. Of course, this kind of tools, I will not say it's push and play or play. You know, it's really you'll need to get involved into it. And but the nice thing is that there's a team at CEA that is here to help and to answer the questions through the GitHub. So here are some references, and let me thank my colleagues, like specifically Olivier Bichler, who is actually leading the N2D2 team, together with David, Vincent, Thibaut, Johannes, and Marc also. They all are, and they are more than that, but they are the big guys behind the N2D2 platform. So I think I have finished. So if you have any questions.
Thank you. It was very impressive. Thank you, Christian. I have directly a question from me. So can I, if I would be a small company, an SME, could I also contact, when I would like to use N2D2, could I contact these people? Are they open for information sharing?
Yes, of course. I mean, the best way to get into N2D2 is just like any open source thing, is to try by yourself and see. And then obviously you'll find some rough edges. That's normal. And then depending on whether you really want to design a specific application for the embedded world, for example, then you'll probably want to go further on. And then, of course, through the GitHub or directly through our emails, you can contact us. And we'll be, we are collaborating in various ways. We are collaborating with through direct collaborations with SMEs or even big companies, or we also collaborate through European or national projects, or any kind of, well, we open to any kind of collaboration, really.
Great. That was, now I let the audience talk because thank you, Christian. That's from Peter van der Linden. Thank you, Christian, for this presentation of an impressive tool. Your partner slide mentions the DGA. Would you have some communicable details about their plans with respect to your system? I mean, can you share some information?
Some information on DGA?
Yes, what they would do basically. What they do with your system, for example. Is that shareable or is it confidential?
If it's the DGA that I think it is, Direction Générale de l'Armement, I think it's highly confidential.
Okay, let's leave it. Next question. Is there already a developer community going beyond CA?
Yes. Sorry?
Yes. We go to the next question. Is there already a developer community going beyond CEA? Is there already a community of developers?
Well, yes, it's well. Let's be honest. There is a community of developers, but in the realm of neural networks and deep neural networks frameworks, it's kind of difficult when you are sitting besides giants like Google and Microsoft and the others. It's really tough because, of course, the people they go to, they go to the community that's the biggest, and then of course it leaves the other ones, even if they are valuable, difficult to get. Also, the goals, the overarching goals of N2D2 are really different from that of generic platforms. It's really focused on people that actually they have an idea of building a specific chip or specific system, which will mix software and hardware. If there's no hardware involved or no specific hardware involved, I think N2D2 is not better than any other frameworks. It really shines when you are targeting specific hardware.
Okay, thank you. Yeah,
the community is growing, but the community in hardware is much smaller than the communities on GitHub on software. It's different. It's not reactive. Also, the time frames are different. Building a chip, it's a matter of months. FPGAs can be a few weeks, but if you're really going for a chip, it's a matter of a few months. So it's not like compiling some lines of codes and testing and recompiling.
It's different. The different community. Yes, at the time now ran us out of our fingers. It's the German saying. The time slipped through our fingers. It's already 4 o'clock, so I know we have to today going to an end. And here's again Dimitris. He says, excellent talk. Thank you, Dimitris, for being so supportive. And I would like to invite you next week again to the cafe. And thank you very much. Next week, we have Matthew Zinn from IBM Research in Ireland. And it will be next Wednesday at 3 p.m. And I'm looking forward towards robust and privacy preserving AI. That's the title which we're going to have from Matthew. And there will probably also become something on the open call of the AI for You platform, but it's not yet clear. So let's wait. And you will receive, as always, invitations. If you don't want to have an invitation anymore, just drop an email to me. And I'm looking forward to welcome you all again. Thank you, Christian. Thank you again. No? And beside all the technical problems, thank you.
Yeah, it's all right.
Yes. And stay healthy, no?
Yeah, take care. Everybody take care.
Bye-bye.
Okay, bye-bye.